Hello and welcome back to PC Retro Programmer. Recently on the channel we've been attempting to get a linearly addressed graphics mode in CGA. This is more of an academic exercise than anything. We're not anticipating getting a really useful mode out of this because the performance is certainly going to be very poor. Very early on we recognized that in order to get a linearly addressed mode at all, we'd need the CGA card to read data from the second bank of video RAM for the entire bottom half of the screen. And this is problematic because the way that the CGA card is wired up, this would mean that we'd need the CRTC to assert row address 1 for the entire bottom half of the screen. And that just seems hopeless. So our strategy has been to break each raster line on the screen up into two shorter CRTC scan lines, one of which is blank on the right hand side of the screen, and this would have row address 0, and that would mean that the following scan line, the one that's not blank where all our pixels are displayed, would then automatically have row address 1. But along the way we've encountered a number of CRTC glitches which are making life a little bit difficult for us. So that's actually the topic of today's video. We're going to investigate these glitches a little bit more systematically to see if we can understand exactly what's going on. This is the way things looked at the end of the previous video. We set the display up so that we had 32 characters displayed across in the horizontal direction, and we filled the first bank with cyan and the second bank with magenta, so we'd be able to see where we were reading data from. And in addition to that, we actually put 32 white characters at the beginning of the second bank, so we'd be able to see when we were reading data from the very beginning of that bank. And actually we expected at this point to have a single white scan line on the screen, but instead, as you can see, we have 31 characters of magenta followed by just a single character of white. And what this suggests to us is that the address that we're reading from in the second bank is off by 31 characters from what we expect. In fact, what must be happening is it must be reading the final 31 characters of the second bank, wrapping around to 0, and then reading just the first character of the second bank. That gives us the white character that we can see. Now, on the previous raster line, we had things set up with two scan lines. One is the normal one with 32 characters displayed, and this should actually be the final 32 characters of the first bank. And once we finish that scan line, we would expect the CRTC to update the address, and it should wrap around to 0. So we should at this point be reading from address 0 in the first bank. And then we have a second scan line on the right hand side of the screen, also row address 0, so data should still come from the first bank. And we set horizontal displayed for that scan line to be 1, so we should see a single cyan character on the right hand side, and indeed we do. In between, by the way, we have a little CRTC glitch. You can see half a character of cyan and half a character that's blank. By default, the Hitachi CRTC that we're using should blank the final character of any scan line, and so we should actually expect an entirely blank character here, but for some reason there's a small glitch. That's the least of our problems at the moment. The more important problem is why we're reading data from 31 characters before the end of the second bank once we start switching to data from that bank. And the theory, my theory, is that the final scan line that's read from the first bank is not updating the address when it finishes, and so that puts us 32 characters behind where we expect to be. That additional character on the following scan line on the right hand side of the screen, that is updating the address by 1, and so that's why we end up just 31 characters short of the end of the second bank when we start reading data from that bank. So we get 31 characters of magenta, wraps around to address 0, and then we get a single character of white from the beginning of that bank. So this is obviously not what we want, and we have to investigate what could possibly be causing this. In order to try and get to the bottom of all of this, I've written some straightforward code, but it's not designed to run on other hardware. There's some of the settings here that might affect certain monitors and may even destroy some. So for that reason, I've not put this code into my GitHub repository, and I certainly don't recommend running it. My monitor is fairly resilient and handles this just fine, but for example, this code makes no attempt to maintain horizontal sync properly, and there are various other issues with it as well. The first thing it does is change into CGA mode 4, and I'm actually going to stick with the standard 2 scanlines per character instead of switching to 1 scanline per character like we did for the linearly addressed code. But I am going to change some of the other screen parameters. For example, I'm going to have 2 scanlines per raster line for every raster line on the screen. Basically, each of the scanlines is going to be half the width of the screen. And what this is going to mean is that we're going to have row address 0 on the left-hand side of the screen and row address 1 on the right-hand side. So in other words, all the data for the left-hand side will come from the first bank, and all the data for the right-hand side will come from the second bank. Now, before we set up any screen geometry, I'm going to put some data in the first bank, and I'm going to alternate between white, magenta, and cyan over and over again. Basically, each character is going to have a different color to the one before it and the one after it. So this will mean that we can distinguish the individual characters on the screen. By the way, 8192 is not evenly divisible by 3, so there's actually one character left over at the end of the first bank, and I just make that white because that would be the next color in the sequence. So that fills the entire first bank, and the second bank I'm just going to leave as all zeros. It's just going to display as black. So in theory, what this code should do is display alternating colors on the left-hand side of the screen and black on the right-hand side. Now, it won't quite work out that way in practice because I'm not going to maintain horizontal sync properly. There'll actually be parts of the screen that are shifted horizontally with respect to the rest of the screen, and this is going to mean it won't look quite right. But at least we know what it should look like if we were maintaining sync, and that should be enough to allow us to interpret what we see. Now, in order to get the screen geometry correct, I need to take into account that I'm burning through scan lines at twice the normal rate. I'm using 2 scan lines per raster line, and so that means I get through a frame in half the time, and so the frames will actually be repeated twice on the screen in the vertical direction. So in order to handle that, I'm going to change the vertical adjust value from the normal value of 6 down to 3, because we're going to hit vertical adjust twice on each CRT frame, and we want to keep the same number of scan lines vertically that we need for CGA monitor. Now, the other thing I'm going to do is to set the horizontal sync position once and for all to 15. And this is going to have the effect of giving us 2 sync pulses per raster line. Now, my monitor handles that just fine. It ignores the first one, and only the second one causes a horizontal retrace. Now, we will see a blank region where the first sync pulse is. By the way, that's fairly wide compared to the actual sync pulse that's sent to the monitor, but that's neither here nor there. And then we enter our CRT loop, and this is where we deal with the individual scan lines. The one on the left-hand side of the screen is going to be 28 characters wide in total, so that means we set the horizontal total to 27. Remember, it always adds 1 to this value. And the scan line on the right-hand side of the screen is going to be width 29, so a horizontal total value of 28. Now, on that first scan line on the left-hand side, I'm going to set the horizontal display to 0. Now, that won't take effect straight away. It will take effect on the next scan line on the right-hand side of the screen, and that'll cause it to not display any characters. Not that there was anything to display anyway. That's row address 1 on the right-hand side, and that's the second bank, which we didn't put anything in. Then on the right-hand side, I set the horizontal display to 28. Now, at this point, it would have been 0, and so no characters are being displayed. And so this is actually not going to take effect immediately either, but it will mean that characters get displayed on the next scan line on the left-hand side of the screen. But at some point on that scan line, we set the displayed back to 0 again, and this is never reached. So actually, it would just keep displaying characters all the way across that left-hand scan line. Now, this situation should be vaguely reminiscent of what we did in the linearly addressed code, especially for that final raster line where we were taking data from the first bank. There's a couple of differences here, of course. We've got 2 scan lines per character, and we also have 2 scan lines per raster line for every raster line on the screen. Now, the idea is that we're going to modify some of these parameters and see what effect that has on the CRTC. So in particular, these horizontal total and displayed values, we're going to change those. In particular, the horizontal displayed is going to be set to either something less than horizontal total, equal to, or greater than, and we're going to see what the various combinations do. And actually there's really quite a variation in how the CRTC responds. Now you might be wondering why I'm expecting horizontal sync issues other than the fact that there are 2 sync pulses per raster line, which I've already explained my monitor handles just fine. After all, we've got 28 characters for the first scan line and 29 characters for the second scan line on a raster line. And so that gives us a total of 57 characters per raster line, which is actually what we want. So where is the issue? Well, the problem is we can only maintain this when we can actually poll for an active region on the line. And this is not going to be possible in the vertical blanking region. There is no active region there. And so this code stops running and we're just stuck with whatever these parameters were down here. In particular, we would have 29 characters total for each scan line, and that's going to give us effectively 58 characters for each raster line, which is one more than it's supposed to be. So basically this means that at the beginning of each frame we're going to get some distortion as it comes back into sync. And we're also going to see the bottom half of the screen shifted horizontally with respect to the top half due to the loss of horizontal sync in between the 2 frames that are on the screen. Anyway, let's run this code and see how it looks, and hopefully we can make some link between what we see and what we saw in the linearly addressed code that we wrote. Well, this is what it looks like, and at first glance is a bit wild and hard to interpret, but actually it's relatively straightforward. This is the image on the left-hand side of the screen here, and actually this just belongs on the left-hand side of that. This is the right-hand side of the screen curled around here, and it's all black. And of course the curve is happening because of a loss of sync in the vertical blanking region, and it sort of recovers and eventually straightens up. And similarly, there's a vertical blanking region in here, and the same thing happens. It curves around and then eventually straightens up as it comes back into full sync. Now, the good thing about the second copy of the image at the bottom here is we can count characters, and we see 14.5 characters before the horizontal blanking region, which is a little bit odd given that we set the horizontal blanking to start at 15. And this continues for 10 characters across, and actually we can just look up here to see how it continues. And then there's a half character, 2 full characters, and then another half character. So in total we get 27.5 characters. And on the left-hand side of the screen, we actually set the horizontal total to 27. So it's displaying an additional half character. And this is precisely the glitch we've already seen, where instead of blanking the final character, it gives a half character. And it seems that this happens when the horizontal displayed value is not reached. So at some point along here, we set it to 0. And of course that value is never reached. Horizontal total is actually reached first, and so instead of blanking that final character, it just displays the extra half character. But otherwise everything here looks pretty much as we expect. This is the pattern we put in video RAM. So now we're going to make a little change to this and see how it differs. Instead of having horizontal total of 27 plus 1 on this side and 28 plus 1 on this side, we're going to change it to 28 plus 1 and 27 plus 1 and just leave everything else the same and see what difference that makes. This is what it looks like now. Obviously we have stripes, and moreover we have 3 full characters between the 2 half characters at the end of the scan line on the left hand side. Now that's not too difficult to explain. We did change the horizontal total from 27 plus 1 to 28 plus 1 on the left hand side, so it makes sense that we have an additional character. Of course we still have the final half character glitch that we already know about, but what's not so easy to explain is the colouring itself. It doesn't matter whether we think of the final character of the scanline as being the last full character, the white one. In that case, we'd expect the next scanline to start on magenta, and it doesn't. Or we could think of the final character as being the magenta one, in which case we'd expect the next scanline to start on cyan, and it doesn't. So what's actually going on here is that it's just repeating the same scanline from memory over and over again. It's not ever advancing the address and reading any of the others. Now this is actually a really cool glitch because it can be used for various demo effects. For example, if you know about Kefren bars, that's roughly how this is done. You just have a single scan line in memory, and as the beam races down the screen, you modify it, and that starts new stripes at various positions on the screen. And the other thing you can do is just modify that scan line in the vertical blanking region and just leave it the same all the way down the screen, and that gives you the appearance of vertical bars going down the screen, which you can move about by changing that scan line in the vertical blanking region. And so that can give you effects like vertical raster bars, for example, instead of the usual horizontal ones. So it's a cool effect, but explaining it is going to be a little bit more difficult. We'll come back to that a little later. Well, this is a third glitch that I've encountered, and this is a really interesting one. This waterfall effect that you're seeing here is really there. It's not an optical illusion, it's not a camera issue. It's actually changing the image every frame, despite the fact that there's nothing changing in video RAM. So this one's really going to require some explanation. So in the first 2 effects that I showed you, we had horizontal displayed set to 0 on the left hand side, and this means that it never actually reaches horizontal displayed. Now in this effect, I've actually set horizontal displayed to 1. Now it's still not reached on the left hand side, but it is now reached on the right hand side, and obviously it will display 1 character, albeit a black one. We didn't put anything in the second bank of video RAM. But I've made one other change to this, and that is the relationship between the horizontal displayed and horizontal total on the right hand side of the screen. Now in the first effect I showed you, I had a horizontal total of 28, which plus the additional 1 gives 29 characters, and I had horizontal displayed set to 28. So in other words, horizontal displayed was reached and even surpassed in that first example. In the second example I showed you, I changed it to horizontal total of 27, which plus the additional 1 is 28, but horizontal displayed was also 28 on the right hand side, and so horizontal displayed was then being reached but not surpassed. And in this effect, what I've got is 27 plus the additional 1 is 28, and now I've set horizontal display to 29, which means that it's never even reached, let alone surpassed. And now it just freewheels with the addresses. It doesn't even seem to reset at the beginning of the next frame. It just keeps incrementing the addresses between frames, which is really bizarre. So in order to show exactly what's going on here, what I'm going to do is change the horizontal displayed value that we set on the left hand side. Remember, in this effect I've set it to 1. What I'm going to do now is set it to 3. So that means it will be displaying 3 characters on the right hand side, and we'll see how that affects the pattern that we see. Well, this is what that looks like, and I wonder how many viewers actually predicted that this would be the result. You can see we have some vertical stripes that are now moving very slowly across to the right. It's certainly not updating every frame. And if you look even more closely, you can see a kind of discontinuity that goes up through the image every now and again. It's a little bit hard to see on camera because there's also some flicker in the vertical direction due to the mismatch of frequency between the monitor and camera, which is made all the worse by the loss of sync that we have, or at least partial loss of sync. Now, what I think is actually going on here is that the discontinuity is the end of the bank in video RAM. So the address is actually wrapping around to 0, and because we don't have a number of characters in the bank that's divisible evenly by 3, we end up with an off by 1 error in our pattern at that point. So that's what's causing the discontinuity. The pattern gets shifted by 1 character across in the horizontal direction at that point. And because the addresses are just freewheeling and changing all the time, this discontinuity is actually at a different position on each frame, and that's why it's moving up. And what I think is really going on here is that every time it reaches the end of a scan line, it's increasing the address by the value that I put in the horizontal displayed register on the left-hand side. So in other words, the address is being incremented by 3 every scan line. Now, if that's all it was doing, then we'd just expect to see a constant pattern going down the screen, because we have a pattern that repeats every 3 characters. But of course, that's only happening until we reach the point where the wraparound in address occurs, and because these addresses are just freewheeling, updating by 3 every scan line without stopping, even between frames, this manifests as a pattern that keeps shifting across by 1 every time that discontinuity goes up through the image. Now, we have to be very careful about the conclusion that we draw. In this particular example, I've changed the horizontal displayed value for the left-hand side from 3 up to 30. And by our previous logic, that should mean that 30 gets added to the address every scan line. But that clearly can't be happening here. If it were, we'd just end up with exactly the same pattern as previously, with the discontinuity going up through the image, now much faster, because we're now increasing the address by 30 every scan line instead of 3. But instead, we see a basically constant image. There's a little bit of jitter here, which I don't completely know how to explain, but I don't think this is important. We do certainly have the pattern repeating every 30 characters in video RAM, so that explains the vertical stripes. But we'd only expect to see that pattern continue until we reach the end of video RAM, where the address wraps around, and then our pattern would be shifted across by 1. And if the addresses were freewheeling, we'd expect to see that discontinuity moving up through the image very, very fast. The fact that that's not happening means that it's not actually increasing the address by 30 every scan line. And with one additional piece of information, we can actually figure out that that's not even possible. These CRTCs are very simple internally. They just have counters which just increment a value every character or every scan line or whatever. And they have comparators which compare those counters with some other value, perhaps a register that we set, or maybe some other internal value. And when those comparators read equal, some event is triggered. And all of these events are just chained off one another in a specific order. So in fact, it doesn't actually add 30 to the address every scan line. We know that because there's no addition circuitry. It can't do that. Instead, what actually happens is it just increments the address every character as it goes across the scan line, and only when it reaches the horizontal displayed value does some comparator read equal, and that triggers an event. And that event is to take the address that it's just counted to and put that address in the register for the start of the next scan line. But in this case, I've got horizontal displayed set to 30, which is too high. It never actually reaches that value. So that event of putting the address that it's counted to into the register for the start of the next scan line, that never happens. So in other words, that address stays the same as the current scan line, and it just keeps using the same scan line over and over again. And so that explains why we have this pattern where the same scan line repeats all the way down the frame. But we also now have enough information to tell what was going on in our attempted linear addressing code from the previous episode. Remember that we had a big long cyan scan line of 32 characters with the additional half character glitch. We had a half character blank, and then we had an additional cyan character, and that was because we had the horizontal display set to 1 at that point. And what we noted is that the 32 characters from the big long scan line didn't update the address, but the 1 character on the right that was sticking out the edge, that did update the address by 1. And the reason is now clear. On the right hand side, horizontal displayed is 1, and this is actually reached. So the comparator actually flips and triggers the address update. But on the left hand side, we had the horizontal displayed set to 1, and this value is never reached. It had already passed that value, and so the event of updating the address is not triggered on the left hand side. And all of this is very unfortunate. We certainly need to set the address for the right hand side to 0 or 1 or something small, and we can't do that on the right hand side. There's not really time, so we have to do that on the left hand side. But as soon as we do that, that means that horizontal displayed on the left hand side is never reached, which causes the issue with the address not being updated. So what we're going to have to do is actually set horizontal display to 32 on the left hand side, and we're going to have to set horizontal total so that the number of characters is actually greater than that value. Otherwise, the horizontal displayed comparator is never actually triggered. And that's going to give us a very, very small gap in which we have to set the horizontal displayed to 0 or 1 or some other small value for the right hand side, and that's going to require a very precise timing, because at the moment we have a lot of jitter going back and forth. So that's what's been causing our problem all along. There's one other question that would be nice to answer, and that has to do with the comparators. They could, for example, go high when the value is reached and then low again when the value is surpassed. And it'd be nice to know whether the address is being updated when horizontal displayed is being reached or when it's being surpassed. And so this code was an attempt to answer that. I've got 27 for the horizontal total on the left and 28 on the right, which gives us 28 and 29 characters respectively, which is a total of 57, which is what you want. And I've set horizontal display to 29 on both sides, so the idea is that it's not even reached on the left hand side, but it's reached but not surpassed on the right hand side. But as you can see, it's just drifting constantly to the left, and the sync is just never maintained. And this is because now there is no non-active region on a scan line. Basically, it's just displaying characters all the time, since the horizontal displayed is always 29. And so the polling code is no longer working. So in other words, it's not actually changing the values from the left to the right hand side of the screen. And so what we really effectively have here is 28 characters on the left and 28 on the right, which is only 56 in total, and this causes this drift by 1 character every scan line. Now, we actually had the same problem in the previous example, and there we had a total of 58 characters across, and for some reason the monitor just handles that. So in that case we're able to get a stable picture and draw some conclusions. So in this particular case, unfortunately, the horizontal displayed is just never being reached, and so we can't draw any conclusions at all about what happens when it's reached but not surpassed. So I'd have to find another way to try and get to the bottom of that. At any rate, I don't think this is important for our linear addressing, so maybe that's a topic for another video.